on two very profound principles. Number one, if it is a the net force must be zero. Number two, if it is a rotating, the net torque must be zero. That's the beginning and end of the theory of statics. F total equals 0. Second, it's not rotating. That's the theory of statics. I make it sort of facetious because, really honest to God, that's all there is to it as far as concerned. Now, apply those two rules, that if something isn't moving and isn't rotating, then the total force must be 0, of course, because otherwise it would be accelerated. And if it isn't rotating, the total torque must be 0. Applying those two rules can lead to some surprising and important results, but the basic theory is utterly trivial. So, what I'm going to do now is examples. Number one, a device you see in front of you. Board balanced on two saw blades. I'm using bricks on a table to masquerade for saw. Board has capital M, and it's centered on the two sawhorses. And they are a distance, what would you say? D. Looks like about a distance D apart. So here's the picture. Sawhorse A, sawhorse B, board. Centered on them, the distance between those two is D. Now it so happens that a lazy painter has left a bucket full of paint. Board, a distance X from sawhorse B. There it is. That paint can has mass M. It's a distance X from the right-hand sawhorse there, sawhorse B. Question, how far out can that paint be before the whole thing is going to tip over? That is, what's the maximum value of X? Before the thing tips over. So, as I do the calculation, I'm going to be moving this thing out here, and we'll see who wins. Me or that. So, what forces act on this? First of all, there's the force of gravity on the board. As far as calculations of torque and force are concerned, you can always concentrate the mass of an object at its center of mass. In the case of the board, that would be right here at the very center. So the force of gravity for all purposes of calculating force and torque is the same as if all of it was concentrated right here. So there's mg, the force of gravity on that, on the board. Now, over here, there's the force of gravity, little m times g, on the paint can. What other forces do you see there? There better be some forces in the upward direction, or else this whole thing is going to go down. Who's exerting the forces in the upward direction? Well, of course, the two sawhorses. There's an upward force due to this sawhorse, let's call it NA, and an upward force due to this one, NB. And I believe those are all the forces acting in this situation. 4 of them. The weight of the board, the weight of the paint can, the normal force exerted by the left-hand sawhorse, and the normal force exerted by the right-hand sawhorse. So far, so good? Now, as long as this thing is not moving, which is what we want, then those forces must add up to 0, and the torques must add up to 0. If you're like me, at this point you say, wait a minute, I understand that the forces are equal to 0. What's torque got to do with this problem? There's no wheels here or anything like that. Well, it's not rotating, but then the total torque's got to be 0. Maybe it's going to be useful information, maybe it's not. As it turns out, very often the torque equation is much more, delivers you much more information than the force equation. So, what do we have? The total forces must be equal to 0. So I've got NA plus NB minus mg minus little mg is equal to 0. So far, so good? Now, how about the torques? Well, I need to calculate the torques with respect to some point. What point shall we use? Somebody says B. Very good idea, but I'm not going to do that. For a reason you'll see in a moment, I'm going to calculate the torques around A. Not a good choice, but you'll see why. Torques about A. By the way, if it isn't rotating, it isn't rotating about any point. And therefore, the total torque must be 0 about absolutely every point. It's your choice which point you want to use, because the torque is 0 about every conceivable point. Well, natural points to use would be A or B, or maybe the center, or maybe where the bucket is. But for that matter, you could calculate torques about some point down here if you want to. They're also equal to 0. I'll come back and talk about that freedom a little bit more in a moment. But right now, let's calculate the torques about A. What do I get? The torque due to NA. What's that going to be about that point? 0. 0. How come? Because it acts right through the point A. There is no lever arm. Tending to rotate the thing clockwise, in the clockwise direction, I see capital Mg out of distance d over 2, and little mg out of distance d plus x, and then tending to rotate it in the counterclockwise direction, nb out of the distance d. So what do we have? Mg times its lever arm, d over 2, plus little mg times d plus x, plus, no, minus, because it's rotating it in the other direction, nb times d equals 0. So there's the torque equation. The sum of those torques got to be equal to 0. What's next? What is the condition that this thing just begins to teeter? Can you think about this? This is actually a subtle point. What is the condition such that this thing just begins to teeter? What can you say about the information on the table at that point? Any idea?
This normal force
A.
The normal force over here is 0 at that moment, huh? As I move this bucket out, the normal force delivered by that brick on the left is actually getting smaller and smaller until there comes a time when it's exactly 0. At that point, I could slide a piece of tissue paper under it or something. It's not actually doing anything at all anymore. It's pretty close right now. But NA goes to 0, that's the magic condition when it just starts to teeter. Everybody agree? So that's the condition that I want for this thing to start to go. What does that tell me? In the first equation, 1 says that NB at that point must be equal to mg plus little mg. Well, of course, at that point, this one is supporting the entire weight of the thing. I plug that into the second equation, the torque equation. Torque equation now says mgd over 2 plus little mgd plus little mgx minus nb times d, which is capital Mg times d minus little mg times d. That must be equal to 0 at the situation where this thing is just about to go. Well, just started to go.
Whoops.
So, that was supposed to be full of pending, but that wouldn't let me do it that way. This is the condition that it just begins to teeter. That's when that end lifts off slightly, no normal force at that end anymore. MGDs cancel. MGD and MGD over 2, so this would make it is -1 plus a half would make it -1/2 when I combine those two together. I was wanting to know the value of x at this point, so mgx equals, pulling this stuff over to the other side, capital MGD over 2, the g's cancel, and the x is then m over m times d over 2. That's as far out as you dare put that bucket. Any further, and you see what happens. You can calculate the torques, as I was saying before, about any point. Every point. About every point, the torques must be 0, but there are sometimes smart points to use and dumb points to use. In this particular problem, I used a dumb point for calculating torques. Let's now use a smart point, which I think somebody suggested. Calculate the torques about, so this would be 2 prime, calculate the torques about B. If I had done business that way, of course it wouldn't change the force equation, but it does change the torque equation. If I calculate torques about this point, what do I get? There's NA now tending to rotate it clockwise, and that's out of the lever arm D, so it would be NA times D. Of course, I'm going to set NA equal to 0 for the condition that it just starts to teeter, but let's keep it in there for a moment. NA times D tending to rotate it clockwise. MG, little mg, what direction does that tend to rotate it? Same, likewise clockwise, so that's mg times its lever arm, which is x, and now tending to rotate it counterclockwise about the point B is capital Mg, so that comes in with a minus sign. Capital Mg and its lever arm is d over 2. So the sum of those is equal to 0. The condition for it just barely to start teetering is that NA equals 0. Therefore, I get immediately MGX equals capital MG d over 2. Again, I cancel the g's and divide by the m, and this says x is equal to m over little m times d over 2. Same equation, but this time I got it in one line. I only needed to use the torque equation. Never had to invoke the force equation at all, doing it that way. What's the moral of the story? You can use any point you want to calculate the torques in statics, but sometimes one point is cleverer than another point. I don't know how you know in advance what is the clever point. I got some thoughts that are always running around in the back of my mind when I'm thinking, what point shall I use to calculate the torques? First of all, if there are a bunch of unknown forces acting at one particular point, then that's almost always the point to calculate torques around. Because if they act right at that point, they don't produce any torque, and if they're unknown, that means I don't ever need to worry about them. So if there are a bunch of unknown forces acting at some point, I'll show you some examples in a moment, then that's probably a good point to calculate torques around. We should have known in this problem that this would be a good point to calculate torques about, because then the only unknown force that contributes is NA, and that we happen to know is going to be 0 at the point where it teeters. If I did it about this point here, the trouble is that then the NA disappears, but NA is something I know something about. NB comes into the problem, does contribute a torque, but NB I don't know, so I have to get NB by going back to the force equation and plug that in. So it was a little bit more awkward to calculate torques around here because that involved NB, which I didn't know. But having said that, if you were programming a computer for it, or somebody who was happy to do a lot of arithmetic, then it doesn't matter what point you use. You might actually wonder then, could I maybe squeeze a whole lot of juice out of a problem like this by calculating, setting the torque equal to 0, not just about one point, but maybe I set it equal to 0 about one point, and I set it equal to 0 about another point, and equal to 0 about a third point. Aren't I piling up a whole lot of different equations that I can work with? No, unfortunately, there is no percentage in doing torques about more than one point. Why is that? Because it's easy to prove. I think I'll let you do this. It's easy to prove that if the sum of the forces is equal to 0, and the torque is 0 about one point, then automatically the torque is 0 about every other point. So if you've already stated sum of the forces is equal to 0, then there's no percentage in doing torques about more than one point. You're just going to get redundant information. Okay? A second example. Let's take that same stick, but this time, same board, but this time we're going to mount it on a wall with a hinge. Here's the hinge, and the board is sticking out like this. And from the end of the board, I attach a guy wire of some sort, a string. And from the far end of this, I hang the bucket of paint. So here's the paint. Remember, it's got mass M. The board has mass capital M. This time I need the total length of the board. What should we call it? Capital L. So, massless string. But I'm worried about that string. It looks kind of flimsy, and I think maybe it's going to break if I stick too much paint out there. So I want to calculate the torque in the string. And now the torque, the tension. So the manufacturer has told me that it can support 27 pounds or so. I want to make sure that it's not getting more than that when I put the pin out there. So calculate the tension in the string. Lest it break. So you got the situation, a board sticking out here horizontally, a string, massless string holding that. Let's say that this makes an angle of theta. I've got the paint with a mass of M, and the board has a mass of capital M, and I want to know what's the tension in that string now. Well, first thing to do, as always, is figure out all of the forces acting on the system. What is the system here, by the way? The system, let's say, consists of the board plus the paint can on the end. What are all the forces acting on board plus paint can. Well, I see gravity, of course, acting at the center for the board, mg. Gravity for the paint can acting over here, little m times g. The tension in the string, of course, pulling along the direction of the string. That's what I'm actually interested in. What other forces do you see here? Well, the hinge is surely exerting some forces on this thing, right? First of all, the tension is pulling back this direction, so that hinge, something or other, has got to be pushing that stick to the right. And I think that's a normal force on the exerted by the hinge. So there's going to be a force this way. Let's call it normal force pushing in that direction. Moreover, for all I know, this thing may be supporting some weight here. It would be a different situation if I had just a stick with just the end of the stick with no attachment here on a greased surface or something like that. Then probably this thing is going to slide down. That hinge is holding it up. So I believe there's also a force here, I'll call it F, because it's kind of like a frictional force, a force in the plane of the surface. But whatever, the hinge is exerting a force to the right and a force in the upward direction, holding that thing in place. Any other forces acting on that system? I guess not. Okay, so number one, it isn't moving, so the total force has got to be 0. Actually, this is a two-dimensional problem, so the forces are going to be 0 vertically and horizontally. Vertical. What do we see? Acting up, I've got little f, and I've got the vertical component of t. Acting down, I have capital Mg and little mg, and the sum of those must be equal to 0. In the horizontal direction, I see n pushing to the right, and the horizontal component of t pushing to the left. That would be t times the cosine of theta. The sum of those has to be 0. Now the torques. What point should we calculate torques about? The hinge, I think, is obviously the position of choice in this problem. Why? Because there are two forces I don't know about and I don't care about that act in the hinge. If I use the hinge as my reference point for calculating the torque, then both of those contribute 0 because no lever arm. So let's use the hinge. That's the obvious place in this problem. In the previous problem, I don't think it was all that obvious what was the good place to use. In this problem, it's pretty obvious that the hinge is the best place to use. Okay, now what do I see here? About the hinge, this is tending to rotate it clockwise, this is tending to rotate it clockwise. Tension is tending to rotate it counterclockwise, so it'll come in with the opposite sign. So what do I have? Mg and its lever arm, L over 2, and little mg, its lever arm, L, and now the lever arm of the torque. Let's see. I extend the line back and drop the perpendicular, so the lever arm is that distance there. What is that? I guess it's L from this right triangle. It would be L times the sine of theta because it's the opposite side. So it's T, the tension, times L sine of theta, and the sum of all those is equal to 0. What was I looking for in this problem? Capital T is the tension T that I wanted to calculate. This equation, the torque equation, by itself is going to do the job, isn't that right? Because I know everything in here save t. So I can solve that for t, and I'll be done. This is very typically the case, that if you've chosen a good point to analyze your torques about, then you never even need the force equation. That happened in the previous problem also. Not always. Sometimes you are inevitably have to use both of them. But very often you could get away with just using the torque equation. So personally, I always analyze the torque equation first, because experience tells me that that may well give me the answer all by itself. So what do I need to do here? T times L sine theta, bringing that over to the other side, is equal to mg L over 2 plus mg L. I guess the L's cancel all the way across, huh? And I get T is equal to little m plus capital M over 2, little m plus capital M over 2 times T divided by the sine of theta. So there's the answer. That's the tension in this string. Suppose that the problem had asked, what is the normal force exerted by the hinge? Then I guess I would have taken the T that I've now calculated from the torque equation, stuff it back into the horizontal force equation, and I could calculate N. What if they asked you what is the vertical force on the hinge? That is the F. I could take that then, take T again, stuff it into the vertical equation, and I could get the vertical force on the hinge. So if what I was concerned about is this hinge going to bust, then we can calculate the forces exerted by the hinge too, but then I really would need to invoke the force equations. See how it goes? Okay, by the way, each of these examples I'm doing is kind of classic examples in statics. So there's a whole class of different things. Obviously, I could pile some other stuff onto this board of various places and make the problem more complicated, but this is the sort of lowest common denominator statics problem. This, the next more sophisticated one. Here comes a slightly more sophisticated one, an example of the whole genre of ladder problems in statics. So this is example number 3. A window washer has a ladder that's 5 meters long. And it so happens it weighs 10 kilograms. I mean, its mass is 10 kilograms. He leaves this up against a window. Not a wise idea, but that's what he did. Here's the ladder. It's 5 meters long. And guess what? He puts the base of that ladder exactly 3 meters from the wall of the house. And here is the window that he's planning to wash. And as you can see, he's leaned the ladder right against the window. Base of ladder 3 meters from wall. Why is that? Nice number. Well, because then this is a 3, 4, 5 right triangle, and the height of the ladder is 4 meters. Okay, what information do I need? Window cleaner has ladder 5 meters long, mass 10 kilograms, leans it against the window, base of the ladder 3 meters from the wall. His mass is 75 kilograms. And it so happens that this window is going to bust if you exert on it a force of 225 newtons. How do I know that? Well, I checked the manufacturer, and he said don't put more than 225 newtons on the dependent glass or it's going to bust. Question, how far up the ladder is this turkey going to get? Got the picture? By the way, I need to tell you that when the ladder is leaning against the window, it has some little rubber rollers up there or something like that, so that, or maybe the window is really slippery. The window doesn't exert any vertical force on it, only an outward force on it. So leaning that ladder against the window, and the force of the window on the ladder is going to be straight out. I think that would typically be true. I need to specify that so it's clear. Okay, tell me what forces act on this system. A man, whoops, where is he? Here he is. And, well, I'll just leave him there for the moment. Okay, tell me what forces act on this system. The system being ladder plus man.
Weight of the ladder.
Weight of the ladder for sure, and that acts as though it was all at the center. So here we are, mg for the ladder. Weight of the man, huh? So m, little m times g, actually wherever he is. Keep going.
Friction on the ground.
Friction on the ground. Which direction, by the way?
Towards the wall.
Towards the wall, that's right. The friction, of course, is holding this thing in toward the wall. If there were no friction, if this was a slippery surface, an icy surface or something, then the ladder would slide out to the left. The friction is holding it to the right. So there's certainly got to be friction acting there. What else?
Is there any tension on the ladder?
What are you calling it? We're talking about the force on the ladder, not the stresses within the ladder now. So at the bottom, however, there will certainly be a normal force acting up, huh? Otherwise, all of the forces are in the downward direction, so there's going to be a normal force there that holds the whole thing up.
Normal force from the window.
Normal force from the window, that's the thing that we're concerned about, so I'm going to call that F, so that we don't confuse it with the normal force from the ground. Anything else? If this had been a really sticky window or something, then there might have been some vertical force exerted on the top of the ladder. That would be a kind of unusual situation, but you can conceive of a problem like that. But here, the force of the window is the force of the window on the ladder, and therefore the force of the ladder on the window is equal and opposite. That force is perfectly horizontal. I think that's it. Those are the forces that are acting in this problem. And what I want to do is find the distance up the ladder that guy can climb, right? Let's label then this distance here x. If I can figure out what that distance was, the horizontal distance to where he is situated on the ladder, if I can figure out what x is, then I can certainly figure out how far up the ladder he's got. Okay. I could write down the forces. Maybe I should. Forces. So 1, the forces. Horizontal. The horizontal forces, I see little f acting to the right, capital F acting to the left. Evidently those are equal. So F minus F equals 0. Vertical. In the vertical direction, what do I see? Acting down, I've got the two weights, and acting up, the normal force at the base of the ladder. So mg plus little mg minus m equals 0. Now the torques. About what point? Base of the ladder is the obvious place to choose in this problem because there are two forces that act there that I don't know about and I don't care about. So best to analyze torques about that point, and those two will disappear. So torques about the base of the ladder, what do I see? First I come to capital MG. That's tending to rotate it clockwise, so let's call that the positive direction. It's mg times, what's the lever arm for that one?
2.5.
At, well, 1.5, isn't it? It's half of 3. Yeah, wait a minute, you got that wrong. It's this distance here that I want, which is half of the base. The base here was 3, so it's 1.5. So it's 3/2 of a meter. And the weight of the guy on the ladder also contributes in the clockwise direction. That would be his mass times G times his lever arm, which is X, the perpendicular distance to the line along which that force acts is X. And now what's tending to rotate it counterclockwise? Capital F, the force of the window, so that comes in with a negative sign. And what's the lever arm for that one?
3, 1.
Is 4. Because if the line along which that force acts drop the perpendicular distance, that's actually the height of the ladder. So, I mean, the height of the window. So it's actually 4 in this problem. You see that? Especially those of you who said it was 3. That was the distance along here, but the line along which the force acts is this horizontal line, and the perpendicular distance is 4. So this is actually 4 equals 0. Now, that window busts. That's the critical point I want. That window busts when F hits the value 225. Let's see, M, the mass of the man, was 75, and capital M, the mass of the ladder, that was 10. And I'm going to use 10 for G also to make life easier for myself. So what do I have? 10 times 10 times 3/2 plus 75 times 10 times X minus 225 times 4 equals 0. That's all I'm going to need. By the way, this is another of those problems where I'm not going to need the horizontal and vertical forces being equal to 0. The torque equation is going to do it all by itself. 4 times 225, 900. 4 2s are 8, and then 4 25s are 1. So this is 900. This is 100 times 3/2, which would be 150. So, and this of course is 750. So 750x is equal to 900 on the other side, bringing it over to the other side, minus 150, which is 900, 800, 750. How about that? The 750s cancel. X equals 1. This guy makes it up 1 meter. No, he doesn't make it up 1 meter. He makes it horizontally 1 meter, which, by the way, is 1/3 of the horizontal distance. So evidently, he makes it 1/3 of the way up the ladder, and at that point, the window breaks. If you now needed to know what the forces exerted by the ladder on the ground, or by the ground on the ladder are, you could put in what F is, 225 newtons here. You could find the frictional force, and from this equation you could get what the normal force acting is too. But we're done as far as this problem is concerned. See how it goes? The most important point for doing, most important reason for doing this problem in detail here, as far as I'm concerned, is to show you how to assemble all of the forces that are acting, and then what's the clever point to choose to analyze your torques about. Okay, one last example, a kind of weird example of statics. But a sort of fun problem too. This is number 4. You've got a bicycle wheel, and it's come up to a curve here, and the curve has a height h. And the bicycle wheel has a radius r and a mass m. The curve has a height h, and I propose to pull on this thing. This is not realistic for riding a bicycle, obviously, but suppose that for some reason I'd attached a string to the center, and I was pulling exactly horizontally on that. I want to know how hard must I pull in order for that bicycle wheel to lift up and ride over the curve. So you got the picture. I'm pulling on the right here, and I pull harder and harder, and finally it starts to lift up. Actually, I think it's pretty clear intuitively that once it starts to go, you can actually ease off a little bit on the force. So the maximum force you have to exert is at the very beginning, just to get that thing to start to go, and that's all we're interested in. Am I going to be able to get this thing over the curve? What's the minimum force that I need to exert there? Okay? So what are all of the forces acting on this bicycle wheel? I've got the force that I'm exerting, of course, the F to the right. I've got the weight of the wheel, mg. Normal force of the ground acting straight up. And now, bad news, I've got the force exerted by the curb on the rim of the bicycle wheel. What on earth is that force? I don't know. What direction does that point in? Some people tell me, well, it obviously points toward the center. I'm not sure what direction it points. But there's some force there for sure. Let's just call it little f, and it's pointing at some direction that I don't know anything about. The resolution to that problem, the fact that I don't know what that force is to analyze torques. About that point, then I never need to know. So this is one of those problems in which I don't need the force equations at all. So let's just go straight to the torque equation and do torque about the, what do you call that, the corner curve. What are the torques about the corner of the curve? So about this point, I see that F is going to tend to rotate it clockwise. What's the lever arm for F? R minus H, right? Because this whole distance here is R, so this distance is actually R minus H. So it's R minus H. That's the torque exerted by F in the clockwise direction. N likewise acts in the clockwise direction. The normal force here, and what's its lever arm? Well, no, it's not R, because the curve is cutting in a little bit less than all the way out there, right? It's this distance, let's call it X for the moment, the distance between here and here, a little bit less than R. Everybody see that? So it's N times X, and then tending to rotate it the other direction is the weight of the wheel, whoops, minus mg, and the lever arm for that one, again, X. Now, what's the condition that this thing just barely is lifting off the ground? Normal force goes to 0, right? I want a condition where I'm pulling it and pulling it and pulling it. The harder I pull, the less the normal force gets to be, until finally it's just barely lifting off the ground. I want N goes to 0. Just to lift the wheel. That tells me then that F times R minus H had better be equal to mg times x, or F, the thing I'm looking for, is equal to mgx divided by R minus H. There's the answer, except I don't know what x is. Now we've got a little piece of geometry to figure out what x is. Anybody see a clever way to do this? Suppose that I completed this right triangle here. The hypotenuse is r, the horizontal distance is x, and the vertical distance is this r minus h. So what would I have? X squared plus r minus h squared equals r squared. What I'm trying to find out is what is x. I could square this out. X squared plus r squared minus 2rh plus h squared equals r squared. The r squareds cancel. I get x squared equals 2rh minus, pulling it on the other side, h squared, or x equals square root of 2rh minus h squared. So put that in for x, and you've got a formula. Question for you. What if h equals r? How hard would you have to pull that?
You can't do it.
You can't do it. From the formula, what happens? In the numerator, I've got x. If I put in r equals h, I would have 2r squared minus r squared, which would just be r squared. Square root is r. So in the numerator, it would just be mgr. But in the denominator, if I try to put in h equals r, I get 0. That force would be infinite. What's going on here? It would take an infinite amount of force to lift that wheel up. Well, yes, it would. If the curve actually went all the way up to there, exactly the line along which you're pulling with force F, there's nothing to rotate that wheel anymore. F is providing no torque at all. So, in fact, I think you can almost imagine that if the wheel was cutting in, if the curve was cutting in right at the horizontal line from the center, you could pull all you like at that point, and it's never going to rise up over the curve. But, okay.
And if it is bigger than R?
Sorry?
If it is bigger than R?
Then it's even more hopeless. Yes. Then is what you have to do is, of course, attach your string up at the top or something like that instead. Then you can lift it up. That's a different problem.
The thing's coming.